Alright, this video is going to be on sequences, and you guys have learned a lot about sequences before, hopefully. And we're not going to do a too much of review on this. We're just going to kind of move forward. So we're going to look a little bit at patterns, and then we're also going to look at how to check the convergence. Whew. All right, so sequences. So if you guys recall, a sequence is a collection of objects. Typically the objects we're looking at are numbers. So a collection of objects with an order and pattern. An alternate definition of this, is kind of interesting to me, is a sequence is a function whose domain is the set of natural numbers. And natural numbers you might think of as counting numbers. So those are positive integers. 1, 2, 3, 4, 5. That's what the natural numbers are. So typically when we think about sequences, we think the first term is this, the second term is this, the third term is this, the fourth term is this, and there's some sort of pattern to help you get from one number to the next. So we're going to look at two types of sequences. One is a converging sequence. And that is when the sequence of terms are going to a specific value. Maybe each term gets a little bit closer to 5. You could say the first term is 4.9, and the second term is 4.99, and then 4.999, and then 4.9999. And all those terms, there's a pattern to those terms, and they'd be getting closer and closer to a value of 5. A diverging sequence is a sequence of terms where they are not going to a specific value. All right, so next we want to look at how we can determine if it's converging or diverging, maybe in a situation where it's not super obvious. The example I gave you is pretty obvious, but they're not always. So here's how we determine. If it's converging, then you're going to find that the limit as n goes to infinity, and n is the term number that you're on, of a sub n equals L. That means that if you take the pattern, a sub n, whenever we write sequences, we usually write a sub n equals something that's written in terms of n meaning the term numbers that you're on. If you could plug in infinity or think about what happens as you go to infinity and you actually get a number there, then you would say, yep, there's a limit, and it's converging to that limit. If it's diverging, then the limit as n goes to infinity of the function would not exist. And that could be that it goes to positive infinity, it could be that it goes to negative infinity, something like that. All right, so we talk a lot about the nth term of the sequence. AKA the pattern or formula. or function. You could have it written a lot of different ways. So we're going to look at a few different patterns. So you in the past should remember a sub n equals the first term plus the common difference times n minus 1. This is an arithmetic sequence. That's if the pattern is that the numbers are consistently adding the same amount each time or consistently subtracting the same amount each time. So if you looked at the odd numbers, 1, 3, 5, 7, those would be an arithmetic sequence because they consistently add 2. So arithmetic. Another that you have studied in the past is a sub 1 times r to the n minus 1. This is a geometric pattern. That's where the numbers are multiplying by the same thing every time. So maybe you start with 1 and then 2 and then 4 and then 8, 16, 32, 64. That would be geometric. We have some more patterns that are kind of popular, but you haven't studied before. Or maybe you just haven't studied them explicitly. So a popular pattern is n squared. This is perfect squares. So 1 squared is 1, 2 squared is 4, 3 squared is 9. So if you see those numbers 1, 4, 9, 16, 25, that's going to be part of your equation when you write out the pattern. If you're writing out a pattern and you're describing what you have as even numbers, you're going to use 2n. If you're writing out a pattern and they want to talk about odd numbers, then that would be 2n plus 1 or 2n minus 1. So 2n means that you're talking about an even number. 2 times anything is going to be even. 2 times anything plus an extra or minus 1 is going to give you an odd number. So that's how we typically represent our odd numbers in these patterns. And then in the patterns, if you want to alternate the signs, you want it to go positive, negative, positive, negative, positive, negative. The way to do that, there's 3 ways. They're all very similar. Is to do -1 to an exponent. So if your exponent was even, the negatives would be multiplying by themselves and they would cancel. If your exponent was odd, then they wouldn't. Another way to do it is -1 to the n minus 1. Then if your exponents are even, the negatives would not be canceling. And then we also have -1 to the n plus 1. So all 3 of these accomplish the same purpose. You would just put them into your equation depending on if you're starting on 0 as your starting term, or 1 as your starting term, or 2 as your starting term. You might adjust your exponent a little bit to make it work in your favor. All right, there's one more thing that we're going to write down in our notes before we start doing examples, and that's about factorials. And these are just number patterns that you're going to have to start to look for to see if you can recognize them. So factorials, and that's not an exclamation. Well, it is an exclamation, but a factorial is an exclamation point. So n factorial really means the product of all positive integers less than or equal to n. So, for example, if we wanted to know what 5 factorial was, that would be 5 times 4 times 3 times 2 times 1. And I did not multiply that out. 20 times 3 is 60 times 2 is 120. So 5 factorial is 120. So if we take this idea further, then n factorial is going to be n times n minus 1 times n minus 2 times n minus 3 and so on, all the way until you get to 1. Also, if you want to look at 2n factorial, then that would be 2n 2n minus 1 times 2n minus 2, and so on, all the way until you get to 1. But you want to be careful, because if I don't put parentheses around this, if I say it's just 2n factorial and I'm not grouping that, then this is technically 2 times the factorial of n. So that'd be 2 times n minus 1 times n minus 2, all the way to 1. So just be careful that you kind of think about what these mean when we use them. A little side note we're going to write over here, we're going to say 0 factorial equals 1. That's a surprising one. There's a proof for it out there somewhere if you are curious and want to look it up. It's also something I could look up for you. We could go over if you wanted. All right, so we're going to do a couple examples. We're going to determine whether the sequence converges or diverges. So for our first example, the pattern that we're going to look at is a sub n equals 3 plus negative 1 to the n. And these little squiggly brackets, you might not have seen those before. It's just a different type of notation. I want to say it's called set notation, but I could be wrong. All right. So for our first term, we just want to plug in 1. So 3 plus negative 1 to the 1. For our second term, we plug in 2. For our third term, we plug in 3. For our fourth term, we plug in 4. So this would be 3 minus 1, that's 2. 3, that'd be plus 1, that's 4. 3, that'd be minus 1, that's 2. 3, that'd be plus 1, that's 4. So this sequence is going to go back and forth between 2 and 4. So I'm going to say, to look at this one to see if it is converging or diverging, I'm going to say the limit as n goes to infinity of 3 plus negative 1 to the n power is going to be 2 or 4, depending on what if your infinity is a positive number or not a positive, an odd number or an even number. So here we're going to say that the limit does not exist, and the reason for that is not because it's positive infinity, it's not because it's negative infinity, it's because it oscillates. I don't know if you guys remember, that's one of the reasons that a limit cannot exist. This is oscillating between two values, 2 and 4. So we're going to say that this diverges. And that's because it doesn't converge to a specific value. So either it goes to a specific value or it diverges. All right, second example, we're going to say b sub n this time, just to be tricky. So this is n over 1 minus 2n. So for the first term, that's going to be 1 over 1 minus 2 times 1. So that's 1 over negative 1. For our second term, that's going to be 2 over 1 minus 2 times 2, so that's negative 3. Our third term is going to be 3 over 1 minus 2 times 3, so that's negative 5. Our fourth term is going to be 1 over 1 minus 2 times 4, so that's negative 7, and so on. So here, if I look at the limit as n goes to infinity of this function right here, we can ignore the 1. The 1 is not going to make much difference when you're plugging infinity in. And if you guys remember doing this, if I plug infinity in on the top and the bottom, these two n's are going to be essentially the same number. So I can cancel those out, and that leaves me a 1 divided by negative 2. So this is going to be negative 1/2. So if I was to extend this pattern for a really long time, I'm going to find that this is going to be really close to the fraction negative 1/2. So I'm going to say it converges to negative 1/2. And if you want to check and see if that makes sense, go ahead and try to find like the 100th term or the 1000th term, and you'll notice that it's pretty close to half. All right, for our third example, we're going to say c sub n this time is n squared over 2 to the n minus 1. So for the first term, that'd be 1 squared, which is just 1, divided by 2 to the first power minus 1, that's just 1. 2 squared is 4. I'm going to go ahead and just do a few of these. 3 squared is 9. 4 squared is 16. Okay, so the bottom is 2 to the second power minus 1. 2 to the third power minus 1, 2 to the fourth power minus 1. Okay, so now I can see there's the numbers, they're not oscillating, so it's not as boring as that first one was. So now I'm going to go ahead and see what would happen if I think about plugging that infinity in. And you have to think about if you plug infinity in and square it, and that's infinity squared, 2 to the infinity. Now these are both going to be getting big. We just have to think about which one's getting bigger faster. And 2 to the n, an exponential growth pattern, grows a lot faster than a parabola does on the right side. So that means that the bottom is getting big much faster. And if you remember, when you have a fraction where the bottom is a lot bigger than the top, then that fraction equals 0. So we're going to say that over time, if you were to, again, find the 100th term or 1000th term or 1,000,000th term, you're going to find that the bottom of the fraction is going to be huge, the top of the fraction not so much. So this is going to converge to 0. Okay, and then we're going to do 3 more examples that are a slightly different type. So for these examples, the instructions are to find the nth term of the sequence. And what they mean when they say that is they really mean write the pattern or write the equation that represents the sequence. So here's our fourth example. The first number is a fraction 2 over 1. Then we have 4 over 3. Then we have 8 over 5. 16 over 7. 32 over 9. And so on. So what you might notice if you look at these top numbers, 2, then 4, then 8, then 16, then 32, is they're doubling each time. And I can see that this one is 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, 2 to the fifth power. So the top numbers are just powers of 2. And then 1, 3, 5, 7, 9, those are just odd numbers. So when I write this formula, I just have to be careful to think about what my starting term is. Am I going to say that this is if you plug in n equals 0, or is this if you plug in n equals 1, or I guess you could start with the fifth term if you wanted. So typically we're going to say this is the first term right here. So if this is the first term, then the top would be 2 to the n, because 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. And then we have to think about which odd version, because we have 2, remember, we have 2n plus 1 and 2n minus 1. Which of those odd versions would give us a 1 on the bottom for the first term? So if you think about 2n plus 1, the first term would be 2 times 1 plus 1 is 3. So we don't want to use that one, we want to use this one. 2 times 1 is 2, take away 1. So then we would say 2n minus 1, and this is going to be if n is greater than or equal to 1. So if you're saying that you start on the first term. We're going to write just an alternate in case you started on 0, saying that 0 was your first one. Then you would say 2 to the n plus 1. So to get 2 to the 1, it would be the 0 term first, so the 0 plus 1 is the first. And then 1 plus 1 gives you 2 to the second. 2 plus 1 gives you the third. And then the bottom part would be 2n plus 1 And that would work if n was greater than or equal to 0. So if you started with 0, the 0 term, and then the first term, and then the second term. So typically I'm just going to say, say that you start on the first term and call it good, unless they tell you something else. But I did want you to see an example where the problem could change a little bit depending on how you start it. All right, the next one is going to be kind of complicated. I want you guys to be able to see a more complicated example. So we're going to look at negative 2 over 1, positive 8 over 2, negative 26 over 6, positive 80 over 24, negative 242 over 120. All right, so if you look at the top, you can see the signs are alternating. Negative, positive, negative, positive. So I know that the top pattern is going to be alternating signs. The other thing, you might look at this and be like, I feel kind of weird. Like I might notice that there's something in common with these numbers, but you might not. So I'm just going to read off some numbers and see if you notice it. 3, 9, 27, 81, 243. So I'm not saying the numbers that I'm looking at, but if you can see, one number bigger than these is the power of 3. So 3 to the first is 3, 3 to the second is 9, 3 to the third is 27, 3 to the fourth is 81, 3 to the fifth is 243. So we know it's alternating signs. We also know that the number on the top is 1 less than a power of 3. So I'm going to say 1 less than a power of 3. I did not leave myself enough room. And then the number on the bottom, I would not expect you to necessarily recognize these. We're going to have to write these out. But the number on the bottom is actually a factorial. So this is just 1. This is 1 times 2. 1 times 2 times 3, 1 times 2 times 3 times 4, 1 times 2 times 3 times 4 times 5. So the bottom is a factorial. And maybe what we should do in class is write out the first several factorials so you guys might recognize them more readily. So if we were to write out this pattern, it's a silly looking sign, then I know n factorial is what goes on the bottom. So that's 1 factorial, that's 2 factorial, 3 factorial. I know that I have 1 less than a power of 3. So that's going to be 3 to the n. That is not an exponent. 3 to the n minus 1. And I just want to check and make sure these are going to give me the right numbers. So if this is the first term, I plug in 1. 3 to the first minus 1 would give me 2. 3 to the second minus 1 would give me 8. And then I have to think about which version of the alternating signs would make me start off on a negative number. So these are the 3 different ways I had to do it. I'm going to go ahead and try the first one and see if that one works. So my first term would be negative, my second term would be positive, my third term would be negative. It's exactly what I wanted. And so that is a good formula for that pattern.